Quantum information processing uses the properties of quantum mechanics, such as superposition and entanglement, to process information in ways inaccessible to standard devices. We consider a particularly promising physical system for information processing, trapped ions. The ions are trapped electromagnetically, and the internal states of the ions store the information. Two long-lived energy levels, representing qubits, are analogous to the 0 and 1 bits of standard computers. The information can be manipulated via atom laser interactions, performing what is called gates. In our paper, we consider an essential information manipulation step, a 2-qubit gate. This gate changes the information state of a second qubit conditionally on the state of the first. The qubits communicate through shared motional modes. For 2 qubits, we have the center of mass and stretch modes. Traditional 2-qubit gates use specific laser frequencies to address particular mode energy levels, or sidebands, such that the information stored by the state of one ion can be used to affect the shared motional mode of both ions. A laser can then change the state of the second ion conditionally on the state of the motional mode, and thus the first ion. In contrast, fast gates excite multiple motional modes and use more complex laser pulse control to reach the target states, as proposed by Garcia-Ripoll, Zoller and Sirac. We consider a fast 2-qubit phase gate which satisfies this evolution operator. A relative phase theta is acquired dependent on the internal states, sigma z, of the ions. Many potential fast gate schemes are restricted or sometimes prohibited by the fixed pulse timing and maximum repetition rates of typical ultrafast lasers. We propose a method to implement fast gate schemes in an experiment, examine possible fast gate schemes using realizable optics, and find a new optimal scheme. Our gate scheme involves a pulse splitting technique using unequal path length interferometers to provide free parameters in the pulse timings, as well as a faster effective repetition rate. A single pulse with high power can be split into many smaller components, with much smaller separation in time than the laser repetition period. This scheme is optimized for gate time and experimental simplicity. It is characterized by the pulse orderings, marked by Roman numerals, and timing delays marked by the tau variables. The scheme is limited by control errors in the pulses, compounded as the number of pulses increase. However, reasonable numbers of pulses provide high-fidelity gates faster than proposed theoretical schemes, and more than 2 orders of magnitude faster than experimentally performed multiple qubit gates. The techniques explored for implementing the 2-qubit gate can be extended to consider more ions, introducing added motional modes. Otherwise, an architecture shuttling ions between separate traps would extend our scheme to be a valuable component of more complex quantum information processing tasks. I hope you enjoy the paper.